In this video, we're going to look at a very famous example of a 1D periodic structure, namely that of a layered stack. So what we're having is we're making sort of a cake of different layers. So let's say we have layers consisting of two materials. We have a higher index material alternating with a lower index material, like this. So this material has refractive index N1, and that material has refractive index N2. And we're going to say that these layers have equal thicknesses, and let's say that they're equal to half a period, A over 2. Okay, so this is the structure that we're studying, and we're only going to look at normal incidence. So if you have a K vector like this, it will only contain, let's say, the Z components, and we're going to say that Kx and Ky are equal to 0. So this is the situation that we want to study. An alternating sequence of layers with equal thickness. Now we're going to study this in steps, and the first thing we're going to look at is the pathological case where the refractive index N1 is equal to the refractive index N2. Because then we're basically in free space, and we know how waves behave in free space, and then we can gradually build up the complexity and look at cases where N1 starts to be different from N2. So what I suggest you do now is pause the video and think a little bit about what the diagram of omega versus K could look like for the case where the refractive index N1 is equal to N2. So what's the band diagram in that case? So we know from Maxwell that if we're dealing with uniform media, that the wave vector K is equal to omega divided by the speed of the wave, and the speed of the wave is the speed of light divided by the refractive index of the material. So if we rearrange this to get omega as a function of K, we get omega equal to C divided by Nk. So this is the relationship between omega and K. This will give us our band diagram. So we have basically a straight line here with slope C over N. Now the thing is, that's actually correct, but it's not complete because there's another branch that looks like this, which is minus Ck divided by N. So where does this branch come from? So pause the video and think about this for a while. So the physical meaning behind this branch with negative K is of course a wave that does not propagate in the plus Z direction, but rather in the minus Z direction. So normally people don't bother with this negative propagation direction because there's simply mirror symmetry between these two branches. But for our purposes, as we will see later, this negative branch is actually quite important. So to get the complete picture, we include waves that are both propagating in the plus Z direction and in the minus Z direction. Right? So this was uniform space. What we're now going to do is we're going to impose some artificial period A. Of course, in free space, uniform free space, that is not really anything that makes a lot of sense, but let's just pretend that our free space is periodic with period A. And knowing what we know about Bloch's theorem, for example, pause the video and see what effect that would have on our band diagram. So we know that in periodic media, we will have also a periodic band diagram, and in the 1D case, that will be periodic with period 2 pi over A in K space. So rather than just having our two bands here at the origin, we will also have copies of that same structure at, for example, minus 2 pi over A, 2 pi over A, 4 pi over A, and so on. So if we just copy this over here, we get another set of branches over there, and then we get another set of branches over there. So we have something that periodically repeats like this. Now, you know, of course, that we have this redundant information here, and that we can also express exactly the same thing by only looking at the interval from minus pi over A to plus pi over A, so the Brillouin zone. So if we only look at the Brillouin zone, So let's see if I can make this a bit more clear here. So if we only look between these two lines here, we can see that our band diagram basically looks something like this. So we have these straight lines that then reach the edge of the Brillouin zone, and then they sort of like fold back at the edge of the Brillouin zone. So this phenomena here of bands which are folding back is called band folding. Okay. But in any case, this is a rather peculiar way of going from a representation that looks like this, because this is what we know what free space dispersion looks like. But we've sort of like artificially turned this into a periodic structure, and then exactly the same information is contained in this diagram. It's just rearranged and refolded such that all the information is contained in the interval minus pi over a and plus pi over a. So this is our basic starting point. What we're now going to do is start from this situation and slowly change the refractive index, and then see what happens if the refractive index contrast increases. But that's a topic for the next video.